להתחיל. So, hello everybody. Today we'll have our second PyTorch tutorial. We'll discuss a bit more advanced topics. So, if before the course some of you were here, and after Shir's great tutorial you advanced to here, hopefully after this tutorial you'll be here. So, we'll cover today vectorization, convolutional-like operations, how to use them and how to implement them. You'll see this in homework 3. Data loading and handling. And if you'll have time, we will also talk about intermediate results and hook, how to save intermediate results. A bit of disclaimer, we have a lot of topics to cover, so possibly some people would not understand everything, but we'll release the slides of this talk and also we'll publish a notebook. So because some things are better like learned by examples, I hope it will be fine. So let's begin with vectorization. What? So let's begin with vectorization. So why do you want like vectorized operations? That's because in GPU we have many like thousands of small cores. Like each green cell in the image is a small core. There are like thousands of such cores. And because of that, many operations can run in parallel if the operation utilizes this design. And vectorized operation utilize this design and are significantly faster than having loops. So which vectorized operation you already know? So element-wise operations like arithmetic operation that Shir talked about in the last tutorial. So if you have two tensors A and B and you add them or subtract them, this will be run vectorically on the GPU and will be very fast. Another line of vectorized operations are linear algebra operation. For example, torch matmul operator, which is also aliased as the at operator. So this can be used to do like matrix vector multiplication. Here we have a matrix n by m, a vector m, and the result would be a vector of size m, a matrix multiplication, and also batch matrix multiplication. Here we have a batch of matrices, a second batch of matrices, and we multiply each batch element with its corresponding batch matrix from the second batch. So this is like the linear algebra operator. And a pro tip is to use broadcasting. So sometimes dimensions are redundant. For example, if you want to add a single row to each row in a matrix, so you don't want to expand the row to the number of rows of the matrix, but PyTorch does this for you. It's called broadcasting. So if you have a matrix A and a row B, and you add them together, what will happen behind the scene implicitly is that B would be expanded to match the size of A, and the result would be of the size of A. This can also be used to add a row and a column. This will generate a matrix with n rows and m columns, and this is like very nice in several situations. And you can also multiply a batch of matrices with a single matrix, and broadcasting will happen also in this example. So you have a batch of matrices, and each matrix in the batch would be multiplied by the second matrix. And this is very fast. Any questions so far? This is like basic. Most of you already knew it. Now we'll continue to a bit more advanced tensor multiplication and summation. This is called torch Einstein. It's practically implementation of Einstein summation convention. So let's begin with an example. Assume we have a matrix and a vector and we want to implement the already known matrix vector multiplication. So how do we do it with Einstein? So first of all, Einstein receives a summation scheme, which we will dig deeper like in a minute, and the operands, the summation applied on. So in this case, we operate on the matrix and the vector. And what is the summation scheme? It's a string where each dimension in each operand is assigned a letter. So in this case, we have 2 dimensions for the matrix, and we assign a letter to each dimension, I for the rows and J for the columns. And it also for the second operand, we assign a letter. But we, like in Einstein summation convention, if a letter is shared between 2 dimensions, it means we apply product, we multiply over this dimension. And finally, we give letters for the result. So, and like the convention is that letters that does not appear in the result are summed over. So here we have I, which is the row, we have J, which is the column, and we multiply J, the column of the matrix, with J, which is the row of the vector, and sum over J, because J does not appear in the result. And we do this for each row in the matrix, for each I. And this happens very fast on GPU. So this is a very simple example. We can do a bit more complex example, which is batch matrix multiplication, which you already know how to do it with Matmul, but we'll see how to do it with Einstein. So this is like the formula that we have. And the nice thing about Einstein, that if you have a formula like this, it's very easy to translate it to a summation scheme. So here we apply on Mat1 and Mat2, and like the summation scheme, we just take the indices from this expression, B and K, BKM, and the result is B and M. So we take a formula, just put the indices in the summation scheme, and that's it. And we can also do this for a significantly more complex example, which cannot be solved with simple matrix multiplication. Like this example, so we have tensors with a lot of dimensions, and we are summing over a lot of dimensions, and like a simple instance, just taking the indices of X and putting them here, of Y putting them here, of Z putting them here, and the output, and this will work. And it will be very fast, significantly faster than for loops. So this is something to know.
I have a question.
Yes.
Is Einstein like a general framework or only for PyTorch?
Yeah, it's a general framework. It exists also in NumPy, and also there is a external package called opt-Einstein, which do Einstein even more optimized in many frameworks. But this is like a very common function used in many frameworks. So any questions about Einstein and what we've seen so far?
Just if I may comment why Ben spent so long about this, because it's not only very convenient to do customized matrix tensor multiplications, but you can also do permutations, and it allows you a lot of flexibility when you handle high dimensional data. So it's implemented for you, very efficient, and it's good to know.
Yeah, and you will also find it useful in your homework 3 assignments. That's a tip. So let's continue to the other kind of vectorized operation, which are sampling operations. So the first operation is gather, which means to sample elements from a tensor according to an index. And what does it mean? Let's say we have a big tensor with some height, width, and channels. Each channel has its own color in this example. And we have a tensor of indices. So for each special location in this tensor, we have an index, which tells us we want to sample here from the first channel, from channel 0, here from channel 0, and channel 1. And what gather do is to sample the elements from the source tensor according to the index tensor. So this will be the samples. We can also do it like to have many channels of index, and like to have multiple samples per location. So let's see how it's done like programmatically. Any question about what gather does in general? The motivation? Okay, so let's begin with an example. Let's say we have a tensor with 4 channels. Yes. Did anyone have a question? Okay, so let's begin with our source tensors with 4 channels, height of 4 and width of 6, and an index which tells us we want to take 1 sample and has the same spatial size as source. And note that the index here should be between 0 and 4. Here 4 is exclusive. So how would we sample it like with a for loop? So we'll create an output array of the size of the index. Then we'll iterate over the position in index, I, j, and k, where I is the number of sample. And we'll just put in output with I, the number of sample I, and at location jk, what's in source at location, a channel index ij, and at special location jk. So this is how it's done non-vectorically with for loops. And in PyTorch you can use gather to do this, but significantly faster. So you gather, you put the source, the data tensor here. Dimension is the dimension of the index, where the index is applied, and index is just a tensor of indices. You can also do this to different channels. So here we sample over the height of the array, and we take 10 samples. So this is gather. Yes.
Yeah, sorry to stop you. So just to make sure that I'm following, sample, like there is no probabilistic.
No. It just you take the element. It's exactly like in the for loop. What gather does is exactly like the for loop. Take the element in that location.
Okay.
Okay. So this will also be used in homework 3. You'll find out where. So this is gather. Gather has yes.
Can I go again about this sampling on the other dimension?
Yes. So what we have seen previously is that we sample over the channels. Here we sample over the height. Okay. So we have index in the height dimension of 10 samples. For each sample, it has an index between 0 and 4, which is the size of source in this dimension. And then in the for loop, we just iterate over like the channel and the width, and over the sample number, which here is j, and we just put in output I, channel I, sample number j, and location like column k, from the source tensor at channel I, at height like at row number index ijk, and column k. So you can do this on several dimensions. We will also publish a notebook with example where you can play with it. So this is really like best learned by examples, by playing with it. So I will continue to gather like it has a twin function, which is called, or an opposite function, which is called scatter. So in gather, we take tensors with many like channels or something, and index and sample it. And scatter is a function that take this sampled tensor, the indices, and spread it back into the original multi-channel tensor. So if gather is a forward, in this case, scatter or scatter add is the backward of gather. And how this is done like programmatically, or like by illustration. So if this is the result tensor from the previous example with the same indices, what scatter will do is to create a blank, a zero tensor, and like add the first element here to the first channel of the tensor, add the second element here, and etc. And
then,
yes,
what does scatter put in the places where are not specified by the index?
what?
If you just take one slide back,
Yes.
like here in the first matrix, the blue one, what does the scatter put in the position 0, 1?
0, like here. It will not add anything. So what scatter or scatter add does is to take this element, the like here the orange element, and to add it, like to accumulate it in this cell in the output array.
So it doesn't create new matrices, it's just
add, yeah. It's mainly an in-place operation.
Okay, thanks.
Okay, so it accumulates and add to an existing array, but usually this other array is initialized with 0, but it's not always the case. So let's begin with like see how it's done with for loops. So we have the source image which is like the sample, it's the output of the gathered sample and index, which is just the same. And now we iterate over the, here it should be 1, it's a typo, I'm sorry. We iterate over like the location in index.
Where should be 1?
It should be 1 here instead of 10.
Mm-hmm.
So we iterate over like the position of index, and we take source and add it, like it's an accumulation to output at that location. And in other location, we do nothing. So this is done vectorically as an in-place operation. It means it changes out like this. This is the syntax, and we'll find it very useful when programming a backward function where the forward used gather. So we can, as before, we can do it like on another dimensions, like before, and you will have time to play with it, like in the notebook we'll publish. There are 2 more functions I will skip. You can find them in the supplementary material, which are the hidden slide of this tutorial. So, any questions so far about vectorization? Okay.
What is the motivation to use gather and scatter?
So the motivation is sometimes you have an oracle which tell you, I want this element, for example, in like, okay, you'll sit in homework 3, you will use gather, I'm sure about it. I try to give an example which does not like tell the solution to the homework, but you get some hint that you want to use a value and you use that value. But I hope this answered the question, but you'll find the motivation in homework 3, I'm sure about that. So let's continue to our second topic, which is convolution-like operation, which is the main topic in homework 3. In homework 3, you will implement from scratch some convolution, the convolution operation and convolution-like operation. So let's begin with a quick recap of terminology. So when talking about convolutions, the first parameter is kernel size, which is the number of elements we have in each dimension. Here we have 3 elements in the height dimension and 3 elements in the width dimension. But we can also specify different number of elements in each dimension. The second parameter is stride, which means what is the distance between windows we take, to do convolution. So this is stride 1. We go 1 in each direction in the height and the width, but we can also do stride 2. This is usually done larger stride 2 or even larger when we want to down sample the feature map quickly to lower the spatial resolution and save computation, save flops in our network. So if we apply convolutions on large images, we have a lot of like computational operator like flops to compute. And if we decrease the size quickly, then very quickly in the network, we do significantly less computation. Another parameter which is less common is dilation, which means what is the distance between the x's, between the elements we take in each block. So this was dilation 1, and this is dilation 2. It means we still have 3 by 3 elements in our block, but they are dilated spatially. We can like have a significantly larger receptive field while still maintaining low kernel size and few computations. And the last parameter I'll talk about is padding, which means what the size of the borders, of empty borders, we add to the image from each side. So this is usually being used when we want to have the same size of feature maps as the output as the input. So here, for example, we have kernel size of 3. We'll have less blocks if we have slide 1 than pixels in this image or feature map, but we can also always add padding of 1 and maintain the number of blocks as the number of like input pixels. Any questions so far about the terminology? Okay, great. So let's continue to how to implement convolutions or convolution-like operations. But before that, I'll give you some examples of how to use it in PyTorch. Like here are a lot of examples, but let's dig deeper in a single example in the fourth row. So here we define a convolution layer, which has kernel size of 3 in the height dimension and 1 in the width dimension, has stride of 2 in the height and 1 in the width, and padding of 1 like at the top and the bottom, and 0 on left and right. Okay, so this is the terminology. It's also used in other convolution-like operation like maxpool. Okay, so let's continue to how to implement such operation. So let's assume we have an image or feature map of size h by w. So the first thing we want to do when implementing such operation is to extract the blocks, which are like in colors here, and have them like in a tensor of blocks. This is the first step. We take blocks and extract them, where each block is a column in this tensor. The second step is to apply some operation on the block. It can be a linear operation, it can be max pooling or something like that. And the last thing is to combine this block back into an image. This is called fold. The common name for unfold in PyTorch is imtocol. This is like the term like in many other frameworks and also in the literature. And the name of fold is called twin. So these are the steps. Yes.
So you should specify to the, for example, unfold function the size of the block.
Yeah, exactly. So in the
right?
unfold and fold, you specify the kernel size, padding, and etc. You tell the unfold which blocks to extract. But we'll see it now. So we receive an image with dimensions, a batch of images, where n is the batch size, c is the number of channels, h is the height, and w is the width. And unfold extract blocks. What does it mean? It goes over the image in like with blocks with the defined kernel size, and it goes over the image with the defined stride and extract the blocks, where each block is a column here. Now note that the block size is C, which is the number of channels, and KH by KW, which is the kernel size. So this is the block, and the number of block we have, it depends on the kernel size, stride, dilation, padding, and etc. Okay, so but the extracted blocks is a tensor where each block is a column, and
Ben, can I have a question again about the unfolding? So, for example, in the picture you show where an example where the kernel has, like, we operate only in one channel, right? But when we will have many channels, it will like stack these column vectors together, right, one under another. So I see that one of the dimension of the output is like C times KH times KW.
It will put them one after the other. I will just talk about how it's aligned in memory.
Okay.
Okay, you will see example of that, but exactly, if you have multiple channels, so in this picture, it will be like here, the other channels. Okay. Okay, so in memory, it's aligned, and in the supplementary material, in the hidden slides, you can learn more about what does it mean, memory alignment. I will show you a bit of example later. It aligned as batch, channels, kernel, and spatial location, even though the shape is just 3-dimension, batch, block size, and number of blocks. So let's see an example. Let's say we have this image with 3 channels, and we apply a fold of kernel with kernel of 2, and the other parameters are the default, stride 1, no padding, and dilation 1. So what would be the shape of this result block? Does anyone know? Anyone?
2 by 2 by 2.
Okay, so
4 by 6.
So the block size would be 3 by 2 by 2, right? Because we have 3 channels and kernel size of 2. What would be the batch size? 2, because like we have two images in the batch. And what would be the block size, the number of blocks? So how many times does this block fit in this image?
6, I guess.
6, no?
6, exactly. So the block size would be 3 by 2 by 2, and the number of blocks would be 2 by 3, which is 6. Exactly. So, yes?
What is the 3 by 2 by 2?
This is the number of channels multiplied by the kernel size. This is the block size as we've seen in the previous slide. So,
okay.
what I said,
Only one image, right?
what?
What I see here, W by H, it's only one image.
Yeah, exactly. So if we want to view the channels as a single dimension, here the channels and the kernel size are in one dimension, you want to separate it. It means that in the memory alignment C comes before the kernel is that you have to like view it where the channels is before kernel size. Otherwise, it will not work correctly. You can read more about why is it that way in the hidden slides later. So how should I view it? Like which dimension should I take in each one? So I can take the batch size from the blocks, the channels from the image. -1 means like fill the gap, compute how many elements should be here, and this is the number of blocks. Okay, so
can you explain again, why do we need this view? What purpose does it serve?
It's very useful many times when you want to apply some operation on each channel separately. So you want the channels to be like in a separate dimension and apply something on like thing in size 2 by 2, but on each channel separately. It's very useful. You will always also find it useful in the homework. Okay, so when you want to apply something on each channel separately, you should extract the channel before the kernel size because of the memory alignment. Okay, so let's continue to talk about fold, which is just the opposite, of unfold. So in fold, we receive a matrix of blocks that we have seen earlier. We receive also an output size, which is the size of the output image or feature map we want to generate. It means the output size here is H by W. The output size does not include like the channels and the batch size. And what fold does is to create an image filled with zeros of size output size. So this is the first step of fold. And like the actual computation is to iterate over the blocks in the output image and in the block tensors, and just add each element, accumulate each element to the corresponding place in the output image. So we'll go over the blocks again, scan the output image and the blocks tensor, and add this blue element here, and later we'll add like other elements to other location. And note that in this accumulation, some positions are sum of multiple value from this blocks tensor. For example, this location, how many elements are accumulated here in this location?
4.
4. This block, this block, this block, and this block. Okay?
So I'm guessing if you do unfold on the output, you won't get the initial input, right?
Yeah, exactly. And you will see in a minute just an example showing that. So let's say we begin with the blocks we had before, like of the same shape as the block tensor we created before, and that the output size is 3 by 4 as before. So we put it in fold, like the output size, the blocks, and the kernel size, which we must specify what is the kernel size. And what it will do is we'll iterate over the blocks and accumulate them. So as you asked before, as someone asked before, like if this is the original image that we unfolded and now fold back, what would be the value in output 1 on 1? Does anyone knows?
4?
What?
4?
4, exactly. It would be 4. Why? Because 4 elements were summed together in this cell, and all the elements are 1. Okay, so doing unfold and fold is not identity. That's very important to remember. You can always unfold and fold an image filled with 1 to normalize it, but this is like outside the scope of homework 3 and this tutorial.
Then again, why did it become this W?
What?
Why it became 1, 2, 2, 1?
So think how many elements were summed in each location. So in the corners, there is only 1 block that covers this pixel. Here there are exactly 2 blocks that cover this pixel, and here there are 4. Okay.
But we saw that you do max pool.
What? I did not do, I just did unfold and fold. I did unfold to this image and folded it back, and this is the result. Okay, so any questions so far about convolution-like operators and unfold, fold?
I assume that here you did fold with the kernel of 2 by 2. Does it
Yeah.
say somewhere?
Yeah. What?
Okay, so this is okay. The kernel.
Yeah, this is like images in the size of the example above. I did not specify that. Okay, so let's continue to our third topic, which is data loading and handling.
Wait, I have a question.
Yes.
So It is useful to for convolutions because in between this folding and unfolding, we will what we'll do with the output of the fold.
You will apply an operator on each block, and the operator is the one that matches like what you need in convolution.
So this will be like the weights of this kernel.
Exactly.
Right? Okay.
Exactly. But you can do other things like max pooling for max pooling and things like that.
Mm-hmm.
So like the main idea is to take an image which is big, extract blocks which are local, and apply a local operation on each block separately and independently. And because everything here is vectorized, and if you implement your operator on each block vectorically, it will be very fast. Okay, so in CUDA and like the native implementation of convolution does not necessarily does that, exactly that, and it's probably more efficient than that, but in the homework solution, that's like the way you should do it. So the third topic is data handling and data loading and handling. So a bit of terminology again. Dataset in PyTorch is a collection of data samples. It can be a collection of images and labels for classification, or collection of pairs of images in other tasks like super resolution. And data loaders are a utility helping to load datasets, examples from datasets. And the main reason people use data loader is because it creates batches, which are easy to work with, like in PyTorch, and they also do it very fast. They can utilize multiple cores in your machine and load the data for the next batch while you are running your network in the current batch. So here's how to implement your own dataset. So in PyTorch, the main dataset you will implement will have two methods you should implement: lang, which specify the length of the dataset, and get item. So here, for example, we have a dataset which will return images loaded from some path and apply a transformation on each image. So here in the init, we just like keep the parameters, the list of images and the transform we want to apply. What would we return in the lang function method?
Number of images in this folder.
Yeah, exactly. Like the length of self-image paths, which is the number of examples we have in our dataset. So this means that when we run lang of datasets, it will give us this value. This is what this magic function does.
What is the transform?
What is what?
Transform.
Transform is a function we want to apply on each image. We'll see in a minute like an example of a transform. It can be augmentation, it can be to convert to PyTorch Tensor from image in other format. And get item is what actually happens behind the scene when you call something with index. So here, what we'll do is to load the image. This, for example, will return us a pill image, which is some format of image. We'll apply the transform on that image. It can be augmentation or something else. And we'll return here a dictionary, where in the key image, we return like the image after the transformation. Okay, so this is very simple. To implement a dataset, you should implement len and get item. And
we don't actually have to return the dictionary, right?
You should return, you can return a tuple of Tensor or a tuple of Tensor and number, which is the label, but in many cases you return a dictionary, for example, image and class or something like that. Okay, so this is like a very popular like convention to return a dictionary. And what will the data loader do? It receives a data set and a batch size and return an iterator. So here the question about what is transform, here the transform is like from torch vision transforms. The first one is a composition of two sequential transformations. One is to take a center crop of size 256, and the second one is to convert the image to a tensor, which usually put the channels at the beginning and convert it like to PyTorch tensor. And here we create the dataset with a list of image paths and the transform. So this is what we have seen so far. And how do we load the data? Usually, we create a data loader which receives this dataset, and a batch size for here, for example, is 32. And how do we use this data loader? It's just an iterator. We can iterate over it. Here, each batch would be a dictionary where in each key we'll have a batch of examples. So for example, what would be the dimension of image here, of the image tensor here, assuming that images are RGB? Does anyone?
32 by 3 by 256 by 256.
And what is the first two dimension you said?
32 by 3.
Yeah, exactly. So this is B. 32 is the batch size, then the number of channels, and then the spatial size. And after you load your data, you can do something, train your network or anything else. Any questions about data loaders?
I missed the part where we use the data loaders of Tensor. This class inherits from Tensor.
It does not inherit from Tensor. Dataset inherits from dataset inherits from dataset. It returns something. It's not necessarily a tensor, but because in our transform the last one is to tensor, it make like here we make sure our image is tensor, like because we apply this transform, and like data loader curates the like multiple returned value from dataset into a batch, and it does it automatically to take, for example, the image key from each element in the dataset and chunk them like in the batch size. Okay, so this will also appear in the notebook. And now we have.
I have a question regarding the shape, which is 32 by 3 by. So this is the shape of image or the shape of the batch?
This is the shape of what data loader, like we iterate over data loader. Data loader, in each iteration we receive a dictionary because in our dataset we return a dictionary. So in the data loader we'll iterate over dictionaries, and in each key data loader will do it for you, like implicitly take 32 examples from the dataset and put them in a batch. So you will receive
is a batch of images.
Yeah, so you will receive batch which has the key image, only this key in this example, and in this key you will have a tensor which is a batch of images of the 32 images the data loader used for this batch. Okay. So it does it automatically for you. And I think we don't have time to talk about hooks, but you'll find it in the slides. It's very useful sometimes, and maybe it will be discussed in later tutorial in this course. Any questions about the topics covered today? Okay, so thank you for taking this tutorial. And next week we'll have, I think, Tali's class about visualization and understanding. So thank you, everyone. And if someone has question to take offline, I will be here before the seminar.